Hi everyone, the channel Easy Lecture welcomes you. In this video we are going to discuss how to convert a voltage into current using operational amplifier. And in this video we are also going to discuss what is the need to convert a voltage to current and what are the electronic devices, why are those electronic devices being operated in using a current source. So all these things we are going to discuss. So before entering into the video, subscribe my channel Easy Lecture. Now we shall go for further discussion. Okay, so before entering into the video, we should understand the concept of voltage and current. So I have discussed a lot about this voltage, what is meant by voltage and understanding voltage and current in one of my videos. So here I am just recalling it. What is voltage and what is current? So current is flow of free electrons. So many people say it as flow of electrons. It is good to say as flow of free electrons instead of flow of electrons. The reason is even rubber, wood and leather, they have atoms, and if atoms are present, definitely electrons are present in it, and those electrons cannot constitute electric current. The reason is the force of attraction between the nucleus and the electrons in those atoms of wood, leather and rubber, they are very strong and they cannot move in a single direction, and they are bound within the atom, within the force of the atom, so they do not constitute any current. Whereas the electrons of metals, they can be separated, and the force of attraction between the nucleus and those electrons can be broken and they can be made free. Made free means that not all the electrons from the atom, only the last electron, the electrons in the last shell. So that is why it is called as a valence band or valence shell, and those electrons are called as valence electrons. And when the valence electrons become free, they are called as free electrons, and these free electrons, when they are made to flow, made to pass in one direction, they constitute current. Okay, if they move in random direction, they cannot constitute current, whereas if all the electrons move in one direction, then it constitutes current. Okay, so in order to make these free electrons to move in one direction, we need a force. That force is called as voltage. So for any material, for any object to move, a force has to be given. It may be stone, it may be water, or it may be any object. For any object to move from one place to another, a force has to be given, otherwise it has to be dropped from a highest position, higher point. Okay, altitude, I am speaking about altitude, right? So that force, here also these electrons, in order to make these electrons to move, we need to give a force. That force is called as electromotive force. Otherwise we have to drop electrons from one point. If the potential difference of there is a difference in potential, then also the electrons move, and that is why it is called as potential difference between 2 points constitute current. Okay, so these are the other names of voltage. So voltage is a force. It is height difference or potential difference between 2 points which make the free electrons to move, and this free movement of free electrons constitute current. So voltage, otherwise called as electromotive force, otherwise called as potential difference between 2 points. For example, let us consider water. So for a water to move from one place to another, either we have to give some mechanical force, okay, in the form of syringe. For example, if we fill a syringe with the water and if we press the piston, the water come out of the outlet and it moves, it flows. Okay, and that flow of water can be compared with, is analogous to flow of electrons. So what flowing of water in the river also constitute current. We call it as water current. Here the flow of electrons, right? And if there is no mechanical force given for the flow of water, then also the water can move if it is moving from a higher altitude to lower altitude. That is why the rivers, that is how the rivers flow. Okay, so here the height difference make the water to flow. Here also the potential difference make the electrons to flow. Okay, so all these are called by a common name called as voltage. So voltage, if voltage is there, then current will be there. Then why do we convert this voltage into current? What is the need? Okay, so here let us consider a battery, a cell, battery cell, which we need to fix in a particular position to make the clock run. Okay, if we do not fix that cell or battery in that particular position, we may have battery in our hand, and if we measure the potential difference between 2 points using multimeter or voltmeter, then also it will show 1.5 volt or something else. Okay, in India it is 1.5 volt of a normal battery, normally using battery. Okay, 1.5 volt, it is showing 1.5 volt, so potential difference is there, but current flow is not there. So when does this current flow? When we fix the battery in a particular position and lock, then the circuit gets completed, only then the electrons flow, which constitute current, and the clock runs. So this is okay, this is the thing. Okay, so for the current to flow, the circuit should be a complete circuit, it should be a closed circuit, it should be like a loop, so it should provide passage for the electrons to flow. If there is no passage for the electrons to flow, then there is no current. Okay, now see here in this slide, here is the simple circuit diagram. Okay, so it is a passive voltage to current converter. As I mentioned, this can be compared with the battery, okay, voltage source, and this is resistor. This circuit, even if the load resistance is not connected, this circuit, when it is closed, constitute current. The current will flow like this. Okay, and when we connect a load in series in this circuit, then the current flows through the load. If the load needs to get operated using the current source, then the current flows and it operates the load. Okay, so here what is the need to convert voltage to current converter? What is the need to use voltage to current converter? What is the need to convert voltage to current? The need is in industries. While discussing about instrumentation amplifier, I mentioned something related to petrochemical industries. There the petrochemical, the oil, they are processed in some area, and the things are monitored in some other point. So the distance between the processing area and the monitoring point is quite away. They are away from each other, and the signals that are measured using sensors have to be transmitted to that point. Okay, so here the sensors, what do? They convert any physical parameter into electrical signal, and the electrical signal is in the form of voltage. Okay, and when this voltage they have to transfer to the measuring point, they may get lost while transmitting through the cable. Okay, whereas if it is converted into current and transmitted through the cable, then there won't be any loss. The reason is, in parallel connection voltage is constant, there won't be any loss. In series connection current is constant, there won't be any loss. But to the depth to which voltage is constant, voltage can maintain itself constant, is different from the way by which the current is maintaining itself a constant. Okay, the thing is, in parallel connection we say that voltage is constant, but in real there will be some amount of loss in voltage, whereas in series connection current is constant, there won't be any loss in current. In parallel connection, although we say voltage is constant, there will be some loss, whereas in current there won't be any loss in series connection. So in order to transfer the signal measured by the sensor to the measuring point, okay, to the monitoring point, if we convert that voltage signal into current signal and transmit, there won't be any loss. Okay, if the distance increase and if we transmit voltage signal, ultimately there is a chance for the voltage signal to get nullified. They may become zero before reaching the monitoring point. So due to this reason, we are converting the voltage signal to current signal. So the electronic device which require current source that can use voltage to current converter. So voltage to current converter convert the voltage to current. Okay, the equivalent current for that particular voltage is drawn, and that is applied to that electronic device which need current, and they are operated. Okay, so here in this circuit, the current that is generated, the current that is flowing here in this circuit, it not only depends on input voltage alone, it not only depends on input resistance alone, it depends on load resistance also. Okay, internal load resistance. If it depends only on input voltage and the input resistance, then there won't be any problem, there is no problem. But here this current depends not only on input voltage and input resistance, it also depends upon the internal input resistance RL, internal input load resistance RL. Okay, so this voltage to current converter is not usable practically. Okay, so this is called as passive voltage to current converter. So we have to go for active voltage to current converter. There are two types of active voltage to current converter. They are floating load voltage to current converter. Another one is grounded load voltage to current converter. First, let us see floating load voltage to current converter. This is the circuit diagram for floating load voltage to current converter. It is basically a non-inverting amplifier circuit. So non-inverting amplifier circuit means we are giving the input voltage source to the non-inverting terminal of operational amplifier. Vin is given to that, and due to virtual ground, the inverting terminal is virtually grounded with respect to non-inverting terminal. So whatever the voltage that we apply to the non-inverting terminal, it will be available at this node. So same Vin is available here. So the concept of virtual ground is clearly explained in inverting amplifier and non-inverting amplifier videos. You can refer to those videos to have a clear understanding about the concept of virtual ground. So I don't want to elaborate about virtual ground here. The voltage that is given here is available here also. So that means the voltage at this point is also Vin. Okay, now we shall go for derivation. The current that is flowing across the load is IL. Okay, and after crossing this node, the current will flow along this branch and also along this branch. But in this branch, so this is the branch of inverting terminal of operational amplifier. The inverting input terminal of operational amplifier has high input impedance, so there won't be any current flowing in this branch. So all the current flows through this path. So whatever the current that is flowing in the negative feedback load resistance is available in the input resistance R. Okay, so when we put it in equation form, I equal to IL. Okay, so these two currents are same. I equal to IL. So that is what I have written in equation form. Now we have to derive the equation for IA using Kirchhoff's current law. Now I am going to apply Kirchhoff's current law at this node. So at this node the voltage is V in, and at this point the voltage is 0 since that point is connected to the ground. So it is 0. When I talk about when I apply Kirchhoff's current law to that node, so the current is moving from right to left. So I write it as V in minus 0 divided by the resistance between these 2 points R. So V in minus 0 divided by R equal to IL, which implies IL equal to V in divided by R. So from this we can conclude that the load resistance is directly proportional to the input voltage V in, which is given into the non-inverting input terminal of operational amplifier. So here the voltage is converted into current. It is if voltage is there, if the circuit is complete, definitely it will give current. So it is more appropriate to say it as voltage driven current source, and this current source IL load resistance can be given to any load, any electronic device which require current for its operation. So this is called as voltage driven current source. Right, now let us discuss about another type of voltage to current converter, that is grounded load voltage to current converter. So I forgot to mention the difference between floating load voltage to current converter, why it has got its name as floating load voltage to current converter. So here in floating load voltage to current converter, the load resistor, it is floating, it is not connected to the ground, so we call it as floating load voltage to current converter. Whereas in grounded load voltage to current converter, the load resistance is RL, it is connected to the ground, and this is called as grounded load voltage to current converter. So this is also basically a non-inverting amplifier circuit with slight modification compared to floating load voltage to current converter. And here we have the input voltage V in, for which the corresponding current has to be produced, and at this point we have the output voltage V naught. Okay, and this node is of important, and the voltage at that node is V1. So at that node means between this point and this point, the voltage is V1. Okay, since the voltage which is connected to the non-inverting input terminal of operational amplifier is V1, due to the concept of virtual ground, the same voltage is available at this point V1. Okay, so V1, and that means at this node also same V1 is available. Here I have mentioned it as V2, so V2 is equal to V1. Okay, so it is not V2, it is V1. So V2 and V1 both are same. Okay, so now we shall go for further discussion. We know that at a particular node, at a particular junction, the sum of incoming currents is equal to sum of outgoing currents. So we shall talk about this node. Here the incoming currents are I1 and I2 and the outgoing current is IL. Okay, due to the voltage, does any current pass through this branch? There is a chance, but here operational amplifier, the input impedance is very large, so it does not allow any current to pass through that branch. So we don't have any current flowing across this branch, so we have only one outgoing current, that is IL. Okay, so sum of incoming currents means I1 and I2 are the incoming currents at that node, and the outgoing current is IL. So IL is equal to I1 plus I2. Okay, so we have written IL is equal to I1 plus I2, right? Now we have to apply Kirchhoff's current law to write I1 and I2 in terms of voltage. To write I1 and I2 in terms of voltage, we have to apply Kirchhoff's current law at that point. So what is Kirchhoff's current law for I1? So I1, so at this node we are applying Kirchhoff's current law. Okay, so this is I1, and at this node the voltage is V1, and at this point the voltage is V in, and the current is flowing from V in to V1, to the node of V1. So we can write V in minus V1 divided by R equal to I1. So I1 is equal to V in minus V1 divided by R. Okay, for I2, how can we write? Here we have output voltage V0 and the current is flowing, I2 is flowing in this direction. So we can write it as V0 minus V1 divided by R. So I2 is equal to V0 divided by V0 minus V1 divided by R. Okay, so that is what we are writing here in this equation. I1 is equal to V in minus V1 divided by R, whereas I2 is equal to V0 minus V1 divided by R. So after solving this, we are getting IL into R equal to, so we are taking, since R is common, LCM is common, okay, the denominators are common, so we can write directly IL into R equal to V in minus V1 plus V0 minus V1. So we can write V in plus V0 minus 2V1. Okay, so V in plus V0 minus 2V1. So I am holding this equation. Right now I'm switching to a non-inverting amplifier circuit. So we know that for a non-inverting amplifier circuit, the output voltage V0 equal to 1 plus RF divided by RI into VI, whereas 1 plus RF divided by RI is the gain of non-inverting amplifier circuit. Okay, and VI is the input voltage, V0 is the output voltage. So this is the equation to derive output voltage for a non-inverting amplifier circuit. Okay, so RF is the feedback resistance and RI is the input resistance. Now we shall apply these things to the circuit that we have. Okay, so what is V0? V0 is as it is. So just remember V0 equal to 1 plus RF divided by RI. Remember this, 1 plus RF divided by RI into VI. Okay, so what are the things that we have as V0, VI, RF, RI in our circuit? Okay, so I told V0 equal to 1 plus RF divided by RI into VI. Okay, so RF is the feedback resistor. So feedback resistance, instead of feedback resistor RF, we have R here, right? And R is the input resistor. Instead of RI, here also we have the same resistor R. Okay, then VI is the input voltage. Okay, instead of having VI, we have V1. Okay, now we shall replace one RF, RI and VI by R and V1 respectively here. So we will be getting V0 as 1 plus R divided by R into V1, and R divided by R is 1, 1 plus 1 is equal to 2, 2 into V1, V0 equal to 2 into V1. Now we are going to apply the value of V0 in the previous equation here. Instead of V0, we have to substitute 2V1. Okay, that we have derived in here. Okay, so ILR becomes V in plus 2V1 minus 2V1. We are cancelling 2V1 and minus 2V1. Finally, ILR equal to V in, which means IL is equal to V in divided by R. So the load resistance that is developed is directly proportional to input voltage that we have applied. Okay, so we are able to derive the current for the corresponding input voltage that is applied. Okay, and the current that is generated here can be used for driving the circuit or driving the devices which require current. So this is voltage controlled current source, and that current source can be used as the source for current controlling electronic devices, and this is otherwise called as transconductance amplifier. These are the other names of voltage to current converter, right? So with this video, I hope you have understood the concept of voltage, current, what is meant by voltage, what is meant by current. So voltage is nothing but it is a force. So for anything to flow, a force is required, and for the electrons to flow, a force is required, that is called as voltage or electromotive force or potential difference between 2 points, and that flow of electrons, it constitutes current. Okay, right? And I hope you understood what is meant by voltage, current, and what are the ways by which voltage can be converted into current, or how to produce voltage driven current source for operating current control devices, and what is the need to do this conversion, and what are the electronic devices. Here LED is operated using this current source. Okay, so what are the devices and where do we require this conversion mandatorily? So all these things I hope you have understood. If you like this video, kindly comment, like, share, and don't forget to subscribe my channel Easy Lecture. Meet you again in another video. Until then, bye. Thank you.